Hello, everyone. I'm very pleased to be here and meet you all people in such a lovely conference. And I have to send my good luck to the guy who practiced in the CTF. So good luck with that. So today we will talk about how I have found and how to find vulnerabilities in third-party kernel modules in Linux, but in a colorful way. So my name is Tal Losos, and I'm a vulnerability researcher at CyberArk Labs, focusing mainly on operating system internals. And except playing with kernels, I really enjoy and practice CrossFit. All right, so what do we have in our menu for today? So first of all, we will review in a very brief way the general architecture of the Linux operating system, but we won't go too deeply into it to not make you fall asleep. Later on, we will discuss a very important thing in a general vulnerability research project, that it's how we can communicate between the non-privileged and the privileged part of our project, and we will talk specifically about the Linux kernel. Afterwards, we will see how, if we're messing up with colors on our keyboard, we can actually trigger some interesting bugs. And lastly, we will discuss and review a newly added feature for mitigation in the Linux kernel, which really reduces the severity of exploiting buffer overflow bugs in the kernel to a mere denial of service. All right, so as you might know already, most of the operating system are divided into two mainly parts, the user space and the kernel space. The kernel space is the actually part of the operating system that is privileged and can able to talk and to interact with the hardware. An example of that could be when the users, for example, request to read a data from a file which is stored on an external device, which then the request actually proceeds to go into the kernel, which then reads the data from the disk and returns it back to the user. When installing an operating system, most of the time, maybe always, you will have the kernel is installed with it. But it doesn't mean that the kernel functionality can't be extended on runtime. Extending the kernel functionality in runtime is done via kernel modules, or in other words, drivers. But why would you even like or want to extend your kernel functionality? An example of that could be to support new hardware devices. For example, new keyboard, mice, camera. Most likely, every type of hardware device that you will want to add for your operating system will require a kernel module or driver that knows how to interact with it. All right, so now that we've reviewed very, very briefly the Linux kernel operating system, let's jump back to my project. All right, so we've conducted a research focusing on the Linux kernel because essentially each bug in the kernel is critical due to the fact that the kernel is always privileged. And one of the best places to hunt for kernel bugs is in third-party kernel modules, because most of the time they're less examined as the kernel itself, and they're always, most of the time, are accessible by restricted users. Exploiting kernel modules bugs can have the same impact as exploiting bugs in the kernel itself. So from just a generic denial of service or to a full local privilege escalation, for example. The way we've done it is by researching and looking for big third-party vendors that actually has open source kernel source for kernel modules and looking up their code, which one of them was OpenRazer. So as you might know, Razer is a big vendor for gaming peripherals, focusing on hardware devices. And if you want to communicate or to configure your gaming peripherals in a Linux environment, you will most likely use the OpenRazer software. So what does it let you do? Again, that's an open source project, and it lets you do basically everything that you see here. It lets you to configure your macros on your keyboard, set custom RGB lights, set your DPI on your mouse, headphones, and it even lets you to configure this amazing Razer mug holder. Yes, that's a thing. Very cool. Every type of device that you see here corresponds to an additional kernel driver that you have to load into the kernel that you will know how to interact with the devices. So only this expands our attack surface very greatly. An example of what we can do with this OpenRazer software is this very easy to join random Swedish flag. One of the prime things that we need to know while conducting a vulnerability research is to know how we can communicate between the non-privileged and the privileged part. And in our case, is how we can communicate between the user space and the kernel space. In Linux, there's multiple ways to do it, which we'll go briefly over the main methods. So first of all, the kernel module or driver can implement the normal read and write in API interfaces, which are then being accessible via the normal read and write syscalls on an exposed device, on /dev, for example. Another way to do it, which is very common on Windows system, is by using the ioctl API interface, where most of the time each functionality is being distinguished by the command parameter, which is then being parsed in the kernel module implementation or driver in most likely a big switch case. The fastest way that we can do it to communicate between the user and the kernel space is by using a shared memory region that can be written and read into from both kernel and user space. In my opinion, one of the more nicest way to do it on Linux is by using the virtual file system, on sysfs, for example. In this way, most of the time, each functionality is exposed on a dedicated file on this file system, which then can be written or written into. It's a very nice way because, again, when you're exposing your kernel functionality on just each function on a dedicated file, it's really easy to communicate and to talk with your kernel devices via just normal shell scripts, because it's very easy to just write and read to files. And for some reason, if you don't like to read and write to files, I wanted to mention that you can use the netlink type of socket, which is just the socket type that you can use to communicate between your kernel space and user space. So our devices are based on sysfs type. So how can we communicate with them? So after loading them into our system, we can check if indeed they have successfully loaded by running lsmod and searching for Razer. Afterwards, because our device drivers are implemented via the sysfs file system, we need to know what's the full path of the exposed files that then we can access to them. For it, we need to know, again, because most of the hardware devices are based on USB devices, we need to know what's the vendor ID and what's the product ID of our device. Razer's vendor ID will be always hexa1532. So in Linux, you can just run lsusb and search for hexa1532, and you will easily find your vendor ID and product ID and everything. And lastly, after we know actually the full path of our exposed files, we can just writing to or read to the files. So here is an example that if we write 1 into the matrix effect wave file, we will actually trigger behind the scenes the functionality that is supposed to light up the wave effect. Which will do this. All right, so now we're moving on to the interesting part, and in this part, I will actually need your help, so stay focused. While researching the OpenRazer software, I encountered this lovely piece of code. This function name is Razer Chroma Extended Matrix Set Custom Frame 2, and its purpose is to actually light up our RGB colors on our custom keyboard. It gets 4 important parameters: the row index, which corresponds to the row on the keyboard that we want to light the RGB colors, start column and stop column that you can actually guess is again the start column and stop column on our row that we want to light up the RGB colors. And lastly, we're getting the RGB data. That is just the hexadecimal values of the RGB value that we want to light up our lovely keyboard. Then, and I have to mention that these 4 parameters are fully user controlled. Based on start column and stop column, we're calculating the row length, which will be how many keys we actually need to light up based on the RGB values. As you might know, each RGB value has red, green, and blue, which is 3 hexadecimal values. So this is why you can see the multiple by 3. and then we're creating a stack variable which is called report, and we're filling up our RGB data by a very simple memcopy operation to this variable. Can you maybe spot an odd behavior or something odd here? I will give you some time. All right, so as mentioned, all of these 4 variables are fully user-controlled. And again, the row length is being calculated by the start column and stop column. So we have a fully control over the size that we copy into the memcopy. And I didn't mention to you that the arguments buffer under the report variable that you can see has actually the length of 80 bytes. So we have a very simplest, very classical buffer overflow vulnerability. So again, because we have full control over the length, our max size that we can give to the memcopy operation is 765. Because the arguments buffer has the length of 80 bytes, we can overflow the stack by 685 bytes, which is quite amazing by its own. As you might know, in open source project, there's a lot of copy-paste between every project, and there's a lot of same logic and algorithms between multiple devices. And while searching more the open source project, I've encountered this piece of code, which is actually purpose is to light up this lovely RGB mug holder. And again, here it's the same functionality that's supposed to light up our mice devices, to light up the colors. Again, same very simple buffer overflow logic, the same concept, the same flow in 3 different functions. And now we can see, let's see a demo. All right, so after that I have loaded into the kernel drivers, I'm making sure that they are indeed loaded into my system. As you can see, the Razer accessory is right there. Because I have my USB device connected, I need to know what's the full path, and here you can see that it's 1532 and everything. Very, very, very simple exploit. I'm just writing vulnerable to the vulnerable function matrix custom frame, writing malicious start and stop column, and if I will run it, I will hopefully crush the system, and it worked. All right, so during the exploit development, we've encountered a newly added feature to the Linux kernel, which was a part of the Fortify source mitigation. Essentially, Fortify source aimed to detect buffer overflows in compilation time and to mitigate them in runtime. An example for runtime mitigation is an example if we have a memcopy operation with a dynamic copy size. Originally, Fortify source came from glibc and got introduced into the Linux kernel in multiple steps, which introduced 2 modes, which we'll call them mode 0 and mode 1. Mode 0 aimed to detect buffer overflows over an entire struct, while mode 1 aimed to detect buffer overflows over on specific member in the struct. Let's have an example. Let's assume that we have this object struct that has 3 members. arg1 in the size of 2 bytes, an array in the size of 6 bytes, and another member called arg2 in the size of 4 bytes, followed by a memcopy operation on the R buffer. If we operate under mode 0 of Fortify source, we can indeed still overflow the R buffer, thus overriding or corrupting or doing whatever we want to the data stored under arg2. But if we operate under mode 1 of Fortify source, we actually cannot overflow even the specific R member in the struct, thus keeping the arg2 very safe and having much safer memcopy operation. All right, so this is the disassemble code of the vulnerable memcopy operation. I'm showing you the disassemble code because, again, the Fortify source mitigation is being inserted in compilation time. So this is our vulnerable memcopy operation with the row length being used as the size for the memcopy operation. And as you can easily tell, there's no any validation on the memcopy operation on the row length specifically. But if we're checking the disassemble code with 45 source enabled, we can indeed see that there's another check that has been inserted on checking row length if the size that we want to copy into the buffer is bigger than hexadecimal of 4D, which is exactly the size that we're allowed to copy into the buffer that we want to overflow it. If we indeed fail this check, that because we want to send to copy more size than we actually can, we will call Fortify Panic, which will essentially crash our driver safely. So Fortify source got introduced into the Linux kernel in 2017 in kernel version 4.13 with mode 0, if you remember, which is overflowing the entire struct for both strcopy and memcopy family of function. Later on in kernel version 5.11 in 2020, mode 1 was turned on for only strcopy family of function, whilst mode 0 was still turned on for memcopy family of function. In kernel version 5.18 in 2021, mode 1 was turned on for both strcopy and memcopy family of function, but for memcopy family of function, only the compilation time mitigation got introduced. So again, while you can still do, as I showed you, overflowing memcopy operation over a specific member in our struct. And very, very, very recently, in kernel version 6.1, mode 1 was turned on for runtime mitigation for memcopy family of function. So now, if you have a kernel version 6.1, you will have both full mitigation against buffer overflow for both for strcopy and memcopy function in your kernel modules. Again, if you're compiling them on a machine with this feature enabled. Just have a note that, again, this mitigation doesn't exist in every operating system, and even exploiting buffer overflow bugs, both in the kernel and both in kernel modules, it doesn't matter. Before, for example, kernel version 4.13, exploiting buffer overflow bugs beyond a denial of service is very, very, very likely to happen, because, again, you have a missing mitigation there. All right, so after that I found the vulnerabilities, I've immediately sent a fixing PR to the open source project, which was merged and released on the very same day. Multiple CVEs were assigned to the vulnerabilities I found, not only in this specific research, on the other open source projects, and I have a couple of more interesting bugs currently under disclosure. And if you want to read more deeply about the vulnerabilities and about the Fortify source mitigation, feel free to reach to the CyberArk Club site and read my blog post that I've written. What's next? So maybe in the near future I will share a very, very, very cool Linux kernel vulnerability I found that has a very, very nice impact. So stay tuned for that. And that's it. Thank you. If someone in the audience has any question, feel free. I've been noted that there's a microphone here. Anyone has questions?
Check. Hello.
Hey.
Yes, I wanted to ask, what is the amount of distribution for the Razor kernel module that you actually exploited?
Again, sorry, can you repeat?
I wanted to ask, how widespread is the Razor kernel module that was used?
Yes, so I have to mention that this is an open source project. It's the mainly and solely program that you can use in your Linux environment. It's not supported by Razer themselves, but I've checked it and there's above 100,000 users for it. So it's quite vast. Yeah. Any more questions? All right, thank you.